me if you want to be polarized.
In this video, we're going to look at polarization. So we're looking at this concept we touched on in the last lesson for that intro, but more specifically what it is and how we can use it. The learning intention for today's lesson is to relate the orientation of the receiving antenna to the plane of polarization for a radio or a television wave, and to use the frequency of oscillation of the electrons for that transmitting and receiving antenna in order to explain the transmission and reception of radio and television signals. So as I said, these will pop up as they come through in the video, just to remind you what the intention is and where it links. So polarization is something that we are generally quite familiar with in terms of glasses. Few people actually know how it works. We just know it reduces glare and it makes glasses good and very expensive. But what is actually going on from a physics perspective is really quite interesting and also quite simple. So firstly, let's start off with radio and television signals. Antennae are used to transmit radio or television waves. Not as common now on things like TVs and radios that we've gone to digital signals, but we're still using the same sort of concepts, but it's just slightly different. So we use these to transmit signals within a certain frequency range according to the size and the form. So for example, AM and FM radio were used in TVs before they went digital, where the AM component was the audio and the FM component was the visual component, and the TV would actually merge the two signals and you'd get your audio-visual signals separately. The simplest type of antenna that we can have consists of two metal rods and is known as a dipole antenna. You often used to see these on TVs, or maybe you've seen them in the retro movies, like what they call the bunny ears. So it'd be like the little V with two single wires and you can move them around. A monopole antenna consists of a single rod placed vertically on a large metal plate. And this is what we usually see on cars all the time. You see the little antenna sticking out from off and around sort of the bonnet area. And the antenna sticking out is the rod, and the roof of the vehicle ends up simulating that ground plate. So it creates this antenna system. Plane polarization involves the restriction of vibrations to a single plane. We saw in last lesson that the plane is defined by the electric field, but we also have a magnetic field component. So depending on which way we're allowing that electric field to travel is what we define as polarizing the light. So if we're going to create a signal, whether that's polarized or not, we produce it by getting electrons that are forced to oscillate within an antenna. So if we have our single rod that's shown in this picture and it's forced to oscillate up and down, that's going to create an electric field that is up and down as it moves. And as time travels and the thing oscillates up and down, we create a wave pattern, and this is where we get our plane polarized electric field component. So that's how we're creating a signal, by moving an electron through the rod. This EM wave is polarized in the same direction as the vibrating particle that created it, and that's because, as we saw last time, it's defined by the direction of the electric field component for the EM wave, but also the electric field is generated in the direction that the charge is moving. So if the charge is oscillating up and down, the electric field component is up and down, and we end up with our wave pattern here. Only an antenna that's orientated in the same direction of polarization, whether that's horizontally or vertically, will receive the signal that's being transmitted. So if an electron in the receiving antenna is forced to oscillate by the electric field of the transmitted radio or television wave, it needs to be oscillated in the same direction. So if you have a creating wave that's moving up and down, and it hits a horizontal wave, a horizontal antenna, if that's oscillating up and down, that electron is never going to move. So therefore it doesn't create a signal. You don't pick up any TV stations or radio stations on that antenna. This links with that learning intention. How can we relate the orientation of the antenna to the plane of polarization? It's just by saying that they need to be the same, and you can explain why, as I just said. If there was a TV channel in the country that was different to one in the city, the reception could interfere with the city one and the country one. Microwave or radio waves can travel very long distances, so this would be a significant issue. you don't want, I mean, it's one thing to tune in and catch country radio, but if the signal is crossing over and you get distortion, you get that old school sort of interference where you can partially see both images on the screen and the audio is all mashed up. We don't want that. So one way that we fix it is we use a horizontally orientated antenna in the city and a vertically orientated antenna in the country. So again, not as common now that we've gone to digital radio, but next time you're driving around in the city or the country, have a look at the antenna directions on people's roofs and see if you can notice the direction change between the vertical and the horizontal orientations. I'm guessing by now you're probably all too young to have ever played with one of these old school bunny ear style antenna. But if you ever did, or if you've seen it in the movies where they're like jiggling the antenna around trying to get a good signal, what you're actually doing is orientating the polarization of your antenna to try and match the signal or the polarization that's being created from the signal source. So you're trying to match it so that the electrons in your rods are getting vibrated in the right directions. When you get that optimized, you pick up the perfect signal. If you're getting a partial polarization angle, you would catch part of the signal, but there's going to be gaps missing, and that's where we start to get our static and our crackling interference. So let's look at this quick little video about polarization and how it works in glasses.
The filtering of light depending on its oscillation direction is called polarization. The light from a light bulb or from the sun has electric fields oscillating in all possible directions. But you can aim that light through a filter like a vertical slit so that only one kind of polarized light can pass through. In the case of a vertical slit, it will only let light through that's vertically polarized. That is, waves whose electric fields are oscillating straight up and down. And if a light wave is horizontally polarized, then it won't be able to pass through the slit. This is basically how polarized sunglasses work. Unpolarized glasses only use darkened glass to absorb some of the incoming light. But polarized glasses have lenses that work as vertical polarizers, blocking out all light except those whose electric fields oscillate up and down. This is particularly helpful when you're on or near the water. When sunlight reflects off water, each reflected ray is partially polarized in the direction that's parallel to the surface it reflected off. So when reflecting off flat water, the reflected ray becomes partially horizontally polarized. And since your fancy sunglasses only let in vertically polarized light, your eyes are protected from the glare that comes off the water.
Okay, so just before I leave you there and we have a look at some of these questions on polarization, I've got an example for you. So in my hands, I've got two polarized lenses. So how this works is that they've basically got tiny little slits cut into them, or filters in a certain direction, almost like minuscule little parallel lines. So that's going to block anything that's coming up and down because it's smashing into those lines and it's not getting through. Anything that comes horizontally though can pass through those little gaps and keep going. So an example of this is if I put my filter in front of you, I just suddenly look really tanned. But if I now take two of them and put them in front of you, again, I just kind of look really blurry and tan. But if I start to rotate both of these polarizing filters, you see I'm starting to vanish. And now I'm completely gone. So if I tilt them back again, I'm about at 45, and now they're parallel again. So all I'm actually doing here is, if you see, like, look at me, I'm not there, I'm there. So what I'm doing is I'm taking two filters and I'm rotating them 90 degrees, and it's like saying, well, I'll cut out the vertical and then I'll also cut out the horizontal and there's nothing left. So this creates a perfect block out of light. And if I shift it, I can get some percentage of light depending on how much I want. So the most basic polarizing lens, which you often have in your glasses, is horizontal. It's probably vertical, because you don't want the light bouncing off the beach to come up and hit you. So it filters that out. There's no good having two that are perpendicular because I just can't see anything. But I may want some sort of angle where I get a limited amount of light, so it's very tinted. So this is an example, and we'll play around with this in class. This is an example of polarizing filters and what they can actually do, and you can see it. Magic.
Tell me pretty lies, look me in the face, tell me that you love me, even if it's fake.